Okay, let's dive right in. Today, we're getting into something pretty fundamental. Relations and mappings, or what most people just call functions.
Yeah, absolutely foundational. And
Yeah.
we're drawing from your notes and a text excerpt that really breaks these ideas down.
Right. And the mission, our goal here, is to just cut through any, potential confusion. We want you to have a really clear grasp of what these terms mean, how they're different, and honestly, why that difference is so important.
hmm And the source material kicks off with something pretty intuitive, something we all kind of get, which is connections. Relationships are just everywhere.
Exactly. Like the examples they give, Mita is the sister of Angkor, or 7 is greater than 2. Simple stuff.
Or even line AB is perpendicular to line CD.
Mhm.
All of those are examples of a relation. Basically, it's just an association, right? A link between objects from two different groups, or maybe even the same group, based on some specific property.
And the sources show a few ways to think about this, like just listing the pairs that are related, or stating the rule that connects them, or even drawing arrows, between the sets. Like if you relate numbers in one set to numbers in another, where the rule is the square root of, you'd link 4 to 2, 9 to 3,
Yeah.
that sort of thing.
Exactly. You end up with a set of these ordered pairs, like
Yeah.
4, 9, and so on. So yeah, a relation is really just any collection of these ordered pairs. It's a very broad idea of connectedness.
Okay, so that's a relation, pretty much any link.
Mm.
What makes a function different? Because that
Yeah.
seems to be where the real precision comes in.
That's the crux of it, yeah. A function or a mapping, it's a very specific kind of restricted type of relation. Not just any relation gets to be called a function.
Why the restriction then?
Well, it boiled down to predictability.
Mhm.
We need functions because they model situations where for any given input, you get one single clear output, no ambiguity.
Predictability. Okay, that makes sense. So how do we get that predictability? What are the rules, the conditions for a relation to actually be a function?
There are basically two key conditions. Two non-negotiables for a relation going from a set A to a set B to count as a function. First one, every single element back in that starting set, set A, has to participate. It must be related to something in set B.
Okay, so nothing gets left out in set A. Every element has to sort of send an arrow out.
Exactly. No orphans in the first set.
Got it. What's the second rule? You said that was the crucial one for predictability.
This is the absolute core difference. Each element in set A must be associated with one and only one element in set B, uniquely.
One and only one.
Right. You cannot have one element in A pointing to 2 or 3 or more different elements over in B.
Okay, so that's the unique image thing they mentioned, like the example in the text.
Yeah.
They said that isn't a function
Correct.
because the first element, poor I5, is trying to connect to both 2 and 4. 2 different outputs for the same input.
Precisely. And that breaks the predictability rule. It creates ambiguity. If it's a function, you put 5 in, you should know exactly what you get out and not have a choice between 2 and 4. Now, importantly, it is okay for different elements in A to point to the same element in B.
Oh, right.
So, for instance, a set like 1, 2, 3, 2, that is a perfectly valid function.
Okay.
Both 1 and 3 are mapping to the same output, too. That's fine.
Okay.
The restriction is purely on one element in A not mapping to multiple things in B. It's about the arrows leaving A.
Yeah, looking at those arrow diagrams in the source really helps visualize this. For it to be a function, every dot in that first circle, set A, needs exactly one arrow coming out of it, landing somewhere in the second circle, set B.
Just one, not 0, not 2 or more. Just one.
Simple rule, but sounds like it has big implications.
Oh, absolutely. That constraint is incredibly powerful. It takes us from just describing any old connection to describing connections that are, well, deterministic, predictable, the outcome for every input.
Which is why functions are so fundamental everywhere, right?
Yeah.
Science, engineering.
Programming, economics, you name it. Anywhere you need a precise input yielding a definite output, you're probably dealing with a function. It lets us build reliable models of the world.
Okay, great.
Yeah.
So let's just quickly recap this deep dive then. A relation at its core is just any association or connection between elements from two sets.
Any link at all, yeah. But a function is a special, much more structured type of relation.
And the key difference, the big takeaway here, is that for a relation to earn the title function, every single element in that first set must be linked to one and only one element in the second set.
That's it. 2 rules rolled into one. Everyone in the first set plays, and everyone plays by mapping to exactly one partner in the second set. no element left behind, and no element playing the field, so to speak.
Right. Understanding that distinction isn't just for maths class. It's really fundamental for describing any system where inputs lead reliably to unique outputs.
And that actually leads to an interesting thought, something for you to maybe chew on after this. Think about cause and effect in the world around you. When you see something happen, a cause, does it always lead to just one specific effect? Or are there sometimes multiple possible outcomes from that single cause? What does that observation tell you about the nature of that relationship between the cause and its effect? Is it behaving more like a precise function? Or is it just a more general relation, something to ponder?
Yeah.